Alright, in this video, we're going to look at two molecules here, so two compounds. So these two compounds are related to each other in a way. So what we have to figure out is, are these enantiomers of each other? Are they diastereomers? Or are they the exact same compound? Are they the exact same molecule? And the only way to do this, there's two ways to figure this out. If they're enantiomers or diastereomers or the same molecule. And there's two ways to figure this out. The first way would be if you're somehow gifted enough to be able to figure this out and rotate these things in your head, in your mind. But if you're like me and you can't do that, so you need like a foolproof, systematic way to do this and get these right 100% of the time, then I'm going to show you how to do that. And the way to do that is to assign RNS. So this is a little bit of a more difficult example. If you want a more detailed example where I go through all the details of how to assign RNS and how to use this method, then go ahead and watch I have two previous videos on that, so I highly recommend you all watching those before you do this more advanced problem. But let's go ahead and get started here. So I'm going to start assigning priorities. So let's go ahead and start with assigning priorities, and we're going to assign RNS. And after we do that, then we're going to be able to figure out if they're enantiomers of each other, diastereomers of each other, or if they're actually just the same molecule. So let's go ahead and get started here. So the first thing I'm going to do is I'm going to go ahead and look at this carbon right there. And that's our asymmetric carbon. That's our stereogenic center, our chiral carbon. And so I'm gonna begin assigning priorities. So which one of these is the first priority? So I'm gonna look at this hydroxyl group. I have an OH, and over here so this is the CHO up top here. So you all have to remember that is actually an aldehyde. So in reality here, I'm going to erase this right there. I'm just going to do this once so you all see what's really going on. So that in reality looks like that. So remember, CHO equals aldehyde. So you have to be able to picture that in your mind. If you can't do that, or if you can't do that, then go ahead and erase it like I did and write out the aldehyde group like that. So that's what we have going on. That's what we have going on right there. That's an aldehyde. So what do we have there? We have a carbon. So that carbon is directly connected to a carbon and two oxygens. Okay, and we obviously have an H over here. And then over here, off to the right, on C3, we have a carbon. So that carbon is directly connected to that carbon right there. And then we also have an oxygen and another carbon like that. Okay, so let's go ahead and assign the priorities. So I'm going to do that in a different color. So what would be the first priority? Well, you have to look at the first atom. So the first atom for all of these is going to be, you either have a carbon, an oxygen, or a hydrogen. So again, so the first atom right here, I'm looking at the first atom right there. So carbon, oxygen, or hydrogen. And we're going by atomic number, and so that's going to be number 1 right there. So that's number 1. Why is that? Again, we're looking at atomic number. We're looking at the atoms that are directly connected to the chiral carbon. Do not look at the entire functional group. If you look at the entire functional group, you're going to think atomic weight, and if you go by atomic weight, you're going to get these wrong. So you have to look at the atoms. All right, so what is next? So what's next here is this. So we have. I'm looking at my aldehyde now. So I'm going to the next molecule. I'm going to the next atom. That's going to be oxygen, and here it's going to be oxygen as well. So now, we kind of have a tie there, right? So we have to move on to the third atom, and the third atom is the tiebreaker because here we have an oxygen. And here we have a carbon. So that third atom right there is going to be our tiebreaker. So by default, then that means this is priority number 2. our aldehyde is priority number 2. All right, and so then by default that leaves us with this entire thing as our priority number 3. And then we have our hydrogen, which is always priority number 4. Okay, awesome. So that is how we do that. And now I'm going to assign RNS to that. So let's go ahead and do that. So I'm going to assign RNS to that. So we're going to go and follow our little clock here, and it just happens to go clockwise there. Again, our hydrogen is already in the back, so we don't have to do any manipulation to this. So our hydrogen is already in the back, which is why we can assign RNS immediately to this guy, because again, that's a stipulation. In order for us to be able to assign RNS, the hydrogen must be in the back. And here it's already in the back, so we can easily just assign RNS to that. And because it's going clockwise, that means that this guy, C2 right there, is going to be R. Alright, so that is R right there. Okay, now bear with me. I'm gonna go ahead and undo all this. So make sure you copy this down, because I'm gonna erase all this and start over with carbon with the second with our second chiral carbon to the right of C2. So I'm gonna start doing C3 now. So go ahead and copy this down if you haven't already, because I'm about to erase it now. Okay. Awesome. So let's go ahead and start with C3. There we go. There we go. Okay, cool. All right. So what do we have at C3? So again, I'm going to do this just for redundancy's sake. So OH. I'm going to have here I'm going to have COH, and then here I have C. And remember, because this carbon right there is directly connected to an oxygen, that's what we're going to go to next. And then we have our next highest atom, which is going to be that carbon from the aldehyde. So there we go. Now we assign priorities, so that's going to be 1. This is going to be number 2 in this case right here. And this is going to be number 3. And that's going to be number 4. Okay, so we have a problem here. Our fourth atom is not in the back. It's on the wedge, so it's actually going to the front. Again, if we do our systematic method, we're going to switch these. So we're going to say that this is 4 now. And this is number 1 now. Okay, so we've switched them. Now our fourth priority is in the back. Now we can go ahead and assign RNS. I'm gonna do my my motion here. So 1, 2, 3, 4. So it seems as if this is going counterclockwise. Initially it is going counterclockwise, which would be S, but because we flip the priorities, we can no longer say it's S, so we have to say that it is R instead. So this guy right here is going to be R right there. So that was R. So if y'all, I'm gonna go ahead and undo this. That way it's not as cluttered. So just keep in mind, copy this down if you haven't already, and keep in mind that was R. Okay, so going ahead and undoing that. And so remember, we had R for that and R for that. Alright, so we have R and R. Now we're gonna, in order for us to compare what we have for this, in order for us to figure out whether this molecule on the right is an enantiomer or diastereomer of the molecule on the left, we're going to have to assign RNS priority again to the molecule on the right. And in the interest of time, I'm just going to go just a tad bit faster, so please try and follow along as best as you can. Again, so I'm going to assign priorities here, and because this is pretty much the exact same molecule. So if you I'm not going to list out all the atoms, so just go ahead and rewind back to the first few minutes where I describe how to do it on the molecule on the left. I'm just going to go just a tad bit faster. So this is going to be our first priority there. This is our fourth priority. This is our second priority here. And this is going to be our third priority right there. All right, so I'm going to want my fourth group pointing towards the back, so I'm going to switch that with number 1, and I'm going to make this number 4. Excuse me. That's going to be, the hydrogen is going to be number 1, and the OH is going to be number 4 right there. So that's what I'm doing. All right, now I can assign R and S. So that's going to be 1, 2, 3, 4. Boom, right there. So it looks like that is R, right? So that's R. However, because we flipped it, it's no longer R, it's actually S. So this is our priority right there. Excuse me, that's our R and S designation. This guy is going to be an S. Okay, so I'm going to erase all that. I'm going to undo it and just write out, just for us to be able to have a little bit more room here. And there we go. And this is going to be S. Now over here on this side, I have, this is my first priority. This is my fourth priority. And let's see, what's our second and third priority? Well, this is going to be our second priority, and this is going to be our third priority right there. Okay, so let's go ahead and do our clockwise, counterclockwise motion. So, and in this case, we can easily do that because the hydrogen is already in the back here. So the hydrogen is already pointing towards the back, which is exactly what we want. All right, so that is going to be, so it's going clockwise, so that is going to be R. And we don't have to do any manipulation or anything like that because we've already have the hydrogen going towards the back. So I'm going to erase all this, and I'm just going to write it out like so. So this is R. Okay, so now we can figure out if they're enantiomers or diastereomers or the same molecule of each other. So, are these enantiomers or are they diastereomers? Well, so going back to the first molecule over here on the left. So as you can tell, we have R, and over here we have S, and we have R. So if these were exact mirror images of each other, if these two were mirror images and were non-superimposable, then the molecule on the left would read SS. So then they would have to be the exact opposite of what's on the molecule on the right would read SS. It would have to be the exact opposite of what's on the left. So in order for this to be an enantiomer, it would have to be S and S, but we don't have that. We have S and R, and because we have S and R, because only one of these changed. So on this one we have R and R, but on this other one we have S and R, and because only one of the chiral centers has changed, that is automatically what the definition of a diastereomer. So in this case, this is a diastereomer. This is going to be a diastereomer. Again, the reason for that is because only one of the chiral centers is changed. Let's do another example. Let me go through another scenario with you. If this had just been, let's say this had been R and S instead, what happened? So what happened? So only one of the chiral centers is changed again. Remember, we have R, S. So only one of the chiral centers is changed. Because of that, again, if this were your scenario instead, it would still be just a diastereomer. So go ahead and erase that. Let's go back to our original scenario. This is R and S. Excuse me, S and R. So because of that, because only one of our chiral centers is changed, that means that this is a diastereomer. In order for this to have been an enantiomer, you would have need to have gotten S and S. So it would have had to have gone from RR to SS. That's the only way you could have had an enantiomer. But because only one of the chiral centers changed, that means it's a diastereomer. Again, we have no plane of symmetry here, so that's another thing you have to keep in mind. If this guy would have had a plane of symmetry, then it would have been a meso compound. Again, but that's going to be another topic. We don't have to worry about that for this problem. So in this problem, yes, this is a diastereomer. Thank you so much for watching. Keep on the lookout for more videos. I'm going to be doing more problems concerning stereochemistry. And thank you so very much for watching.